going to tell us about how private our DPS should be.
Yeah. Yeah, so I'll be giving this talk about, we'll be talking about the PSGD and how private is in implementations. And this is, this is a joint work with other Googlers. Yes. Does this work?
I think it's on.
I think it's on.
Try again.
Is it working? Oh, okay. Thanks. Sorry for the technical difficulties. Yeah, so let me, so I think you've probably all heard a lot about differential privacy already, but since it's quite central to this talk, I'll go through the definition again in more detail. So in differential privacy, we consider the notion of adjacent data sets. So, so I'll define this more precisely in a later slide, but basically, you can think of it like if we have two data sets that differ in a single example, then for differential privacy, we want the algorithm to distinguish between these two data sets. And more precisely, we have the notion of epsilon delta differential privacy for two parameters, epsilon and delta. And we say that the algorithm is differentially private if for two adjacent data sets, X and X prime, then the output of the algorithm on both data sets is similar by a multiplicative factor of e to epsilon plus delta. So basically, if epsilon and delta are smaller, then the algorithm is more private. Yeah. So the usual way of achieving differential privacy when training ML models is to use this algorithm called DPSGD, or differentially private stochastic gradient descent. And this was first introduced in this paper by Abadi et al. In 2016, and is still being used now for training ML algorithms. And yeah, the focus on this talk will be DPSGD. So I'll go through it again in more detail. So to introduce how DPSGD works, I'll first start with the non-private version, which is just SGD, or the mini batch version of SGD. So basically, when we train the model, we first start with a data set with n examples, and we split it into batches, they're called S1 to ST. And we have a differentiable loss function, Fw, and an initial state W0, and an optimizer. And yeah, and then we have this data set that we arrange into T batches, each of size B. And in this talk, I will just assume a single epoch of training, although the techniques that we have can be extended to multiple epochs. Yeah, so in SGD, given these batches of data, we first use backpropagation to compute the gradient vectors. And so we have the per example gradients for all the vectors, and then we take the average over each batch. So we sum up the gradients and take the average. And then we pass these average gradients into an optimizer, and we use this to update the model parameters based on the gradients. And then this will give us a new model state. And we repeat this for T iterations to get a final model state. So this is how we train the model. Yeah. And now I'll describe how we extend this to achieve differential privacy in DPSGD. So again, we start with the batches of data, and then we compute the per example gradients. But this time we will clip the gradient vectors. So we clip them by the L2 norm. So this is to ensure that the contribution of each example is bounded, and this helps to achieve the DP guarantee. And then we take the average of these clip gradients, and we add some Gaussian noise that is proportional, like, scaled based on the clip norm. And then we pass this noise average gradient to our optimizer to give us the state. And we repeat this for T steps to get the final model state. And if you choose the parameters correctly, then you can achieve like epsilon delta dp, based on the parameters. Yeah, and in this talk, we'll be concerned about how to analyze the privacy guarantees of DPSGD. But since DPSGD is pretty complicated, we abstract it to something that we call adaptive batch linear queries, or ABLQ. And we'll be talking about different ways of constructing batches of data from the data set. So first, we assume that we have a batch sampler B, that basically given the data set of size n, it constructs T batches of data. And then we repeat for each of these batches that we have an adaptive query method that constructs a query based on all the previous answers. So in the case of DPSGD, this query will be computing the clip gradients of the examples. And then after computing this, we add we sum up the gradients and then we add noise. So similar to DPSGD, but more abstract notion here. And you analyze the privacy of this mechanism. So yeah, so the main question that we are studying is how does the batch sampler B affect the privacy cost of this ABLQB? Yeah, so I will describe a few types of batch sampling that we consider. So the easiest approach to sampling batches is given the the data set of size n, we split it into equal size batches in the order that the examples come in. So basically you take the first T examples and you form a batch, and then the next T and the first B and the next B and so on. And then this will be we call this a deterministic batch order. Yeah. So this is easy to implement, but in practice it's not so good because if you call the definition of DP, we want to hide we want to distinguish like two data sets when example occurs. So if we shuffle up the examples a bit, then it could help to hide where the example is present during the training. So adding some randomness to the batch sampling will intuitively improve the privacy guarantees. Yeah. So the next type of sampling that we consider is called the shuffle batch sampler. And so in shuffling, basically we consider a simple type of shuffling where we shuffle all n examples and then we split them into batches as before. And this is actually quite common in practice when we run ML training. There are various forms of shuffling that we can consider, like using an additional buffer to shuffle the examples. But for this, for simplicity of the analysis, we just consider global shuffling. Yeah. And yeah, but the privacy analysis of the shuffle batch samplers is actually more challenging because there's some correlation between the different batches. Yeah, so it's actually hard to analyze. And so what people use most commonly in practice is Poisson subsampling to sample the batches. Yeah, I think something like this was described in the previous talk. So basically, for each batch, we independently pick for each example to be included in the batch with the same probability. Yeah, and it's yeah, so each batch should have the same expected size, but the actual number of examples in each batch can differ. So this is actually a lot easier to analyze in practice. So yeah, this was actually first described in the first paper by Abadi et al. On DPSGD. So there they say like they do the privacy analysis using Poisson subsampling, but they also mentioned the paper that in practice for efficiency, they don't actually do Poisson subsampling, but instead they do something like the shuffle batch sampler that we described. And then it was also pointed out in other papers that people often use Poisson subsampling for the privacy analysis, but they don't actually implement it. So there's some gap between the privacy analysis and how it's done in practice. Yeah, and then you can see that in some libraries, they also describe this. this problem. And yeah, so through our literature search, we only found one instance where people say that they actually do Poisson subsampling for sampling the batches. And this is in the Opacus library. But to the best of our knowledge, it doesn't really scale to large data sets because of the way they implement it. Yeah, but we are not experts, so feel free to correct us if we are wrong about that. Yeah, so I'll briefly describe the adjacency notion we use for DP so this will affect how we do the privacy analysis. So, so the commonly used notion is the add-remove adjacency, where we consider the two data sets to be adjacent if they differ by adding or removing a single example. However, this does not really work for the deterministic or shuffle batch samplers because there we need each batch to have the same size. Yeah, and another notion that you can consider substitution, where we replace one example by another example, but this is also not really standard for the Poisson subsampling privacy analysis. So here we will consider what we call the zeroing out adjacency, where we replace an example by a ghost example. And then the analysis is the same for the Poisson subsampling, and it also works for the shuffle and deterministic samplers. Yeah, so I'll give a sneak peek of the results, and there are more details in the paper. But basically, we will consider the epsilon. We define epsilon b delta to be the smallest epsilon, such that the ABLQB satisfies epsilon delta dp. And you can similarly define delta. So for the deterministic batch sampler, we have a plot here of how epsilon varies with the noise multiplier. And for the deterministic batch sampler, there's a nearly closed form expression for delta. So it's quite easy to compute, and you can compute epsilon by binary search. And then for the Poisson batch sampler, there are different methods to compute this. So so one way to do this is to use Renyi DP, which gives us upper bounds on the epsilon and delta. And another way to do this is to use the privacy loss distributions, or PLD, and this actually gives upper and lower bounds, but it's a numerical method. Yeah, but it can give us pretty accurate bounds by controlling like how much accuracy you use. And so the green curve gives the PLD parameters, and the purple one's the RDP. And we see that in both cases, it does better than the deterministic batch sampler. Yeah, and here we have a description of the library we use to compute these parameters that is maintained by our team at Google. So now the question is, where does the shuffling batch sampler fall between these? Because that's what people often use in practice. So here we have the orange line for shuffling that is somewhat in the middle of the two, the deterministic and Poisson sampling. And so an important note is that this is just a lower bound because it's pretty difficult to analyze. And then in our work, we have a new technique to prove a lower bound on the results, but not yet an upper bound. But we can see already that there's like a gap between the epsilon for the shuffle batch sampler versus the Poisson subsampling batch sampler, especially at the low sigma. So this is actually quite bad if you are using shuffling to sample your batches, but you actually use the privacy parameters for Poisson subsampling. So it means that you are reporting higher privacy than what is actually being achieved in practice when you are implementing DPSGD. So you can see that at higher values of sigma, these lines converge. So at some parameters, it's okay to do that, but at different parameters, it might not be. So the key takeaway that we want people to have from our paper is that you need to be very careful when you're reporting the privacy parameters of DPSGD, especially if you're doing shuffling rather than doing the real Poisson subsampling, and you're using the privacy parameters for Poisson subsampling, which is common in practice. Yeah. Yeah, so I will do a brief summary of what we have. So yeah, I will talk about the future steps. So in this work, we mainly give just a lower bound. So yeah, an obvious next step is to find the upper bound for the shuffling privacy accounting. And it's also unclear how to efficiently compute the epsilon parameters for shuffling exactly. And there are also different types of shuffling that we can consider, such as and how to extend our analysis to multiple epochs is also technically more challenging. And yeah, like I mentioned before, there are types of shuffling using a buffer, or when there are multiple epochs, you can also consider variance where we reshuffle for every epoch. Yeah, so it gets more complicated, and there are many variants of shuffling or more general batch sampling that we can consider. And another direction that we're also looking at is to implement Poisson subsampling at scale. So, and to actually run DPSGD using these different types of batch sampling to see how the utility varies depending on the batch sampler and the correct privacy parameters. Because yeah, the type of batch sampling might also affect the utility of the ML training. And yeah, lastly, I also want to mention that there are also some DP methods that don't rely on this privacy amplification. And so it's another direction to consider, such as the DP-FDRL or the DPMF methods. Yeah, so that's the end of the talk, and yeah, happy to take any questions.
I was just curious if some of the mechanisms here actually.
How could I can just slide, click the slide? Oh, there the clicker. Okay, thanks.
Right, our next speaker will be Ying, and he's gonna tell us about Eureka, a general framework for black box differential privacy estimators.
Okay. Thanks for everyone being here. So today I'm going to present our work, Eureka, a general framework for black box differential privacy estimator. So this is a joint work between Malik and my advisor, Vasilis. So our work is motivated by the following scenario. We have a domain expert who knows quite well like how to design a mechanism that can extract useful information over a data set, but he might not know how to show that their design mechanism ensures strong data privacy. So we would like to provide a black box way for the domain expert so that he can empirically estimate how private their mechanism is. So we stick on the black box estimation here because we don't want to make any assumption on the domain expert's knowledge on the privacy. So this enable the domain expert instead of just the privacy expert to contribute to the privacy community. Also, thanks to the previous speakers, I will not recap the DP's definition here, but I would like to share one of my favorite intuition of DP. So it says that a mechanism is DP if there's no algorithm that for whichever neighboring database pair you choose with high probabilities, it cannot distinguish the output distribution with the advantage more than epsilon. So here the privacy parameter epsilon and delta, epsilon captured as how much privacy we could obtain, and delta captures like how much risk we shall take. So instead of just stick on one pair of epsilon delta, we would like to propose a notion called privacy spectrum. Actually, it captures the almost interesting and incomparable epsilon delta to give the full privacy spectrum of the scheme, privacy of the mechanism. So more specifically, the delta of the epsilon is the smallest delta achievable by the epsilon. So as the intuition, to give an intuition, we plot the privacy spectrum of the Gaussian mechanism and the Laplacian mechanism. So take a closer look, we can see that in most of the region of epsilon, the Gaussian performs better than the Laplacian in terms of the privacy. So this interesting observation suggests that the privacy spectrum seems more useful than just a single pair of epsilon delta. So with this concept in mind, we're ready to shift gear to our problem statement. So basically, our problem statement is following. So given a mechanism M, we want an efficient estimator that can provide the accurate estimate of the privacy spectrum. So here, the efficient, we mean that we want the estimator to be run in a polynomial time. And then our good estimate here means that we want to have accuracy guarantee on the output. So the data we want first, the estimator shall only access the mechanism in a black box way. And then second, ideally, we don't want to make any assumption on the mechanism. So the estimator shall give an accurate estimate for arbitrary mechanism. But unfortunately, this is not achievable. So we do the next best thing we can expect. That is to have a minimal assumption on the mechanism. So here, specifically, we mean that we only assume the mechanism's output distribution satisfies some smoothness assumptions. And then the third property is like we want the estimator give a tight estimate of the DP spectrum. The tight estimate here means with probability at least 1 minus something, that with high probability, the estimator's output shall be a tight bound of the privacy spectrum. But unfortunately, this is not achievable due to the nature of the DP, because by DP's definition, the mechanism's input domain shall be all the multi-side over a record universe. That means like you will have infinite many neighboring pair. It is not achievable by a polynomial time algorithm to pick the worst case among them. So we do a relaxation of the DP, which return it relative DP. So it's basically the same as the DP, where the only difference, like we require the distinguisher that the algorithm A here only pick its favorite neighboring database pair from a chosen set T. So this is to capture the reality that usually the domain expert only have fewer data set by hand. So we think it's a reasonable way to circumvent the impossibility. And then also, the thing we can achieve is to have a tight estimate of the relative DP spectrum. So to compare with the previous work, our estimators only require black box access. And our work supports a larger class of mechanism, even support the mechanism with large output space or even the real range. So in terms of the accuracy, our estimator provides a tight bound instead of just the lower bound. This in contrast with the line of work called DP auditing. So now I'm going to move the topic to the next point, that how do we achieve such problem statement? So we write it, the main idea is to reduce the privacy estimation problem to a binary classification problem. So we write it down the expression of the privacy spectrum, and then so for now we just focus on the inside part, the inner part, which we term it as indistinguishability spectrum. So basically, it measures how difficult to indistinguish a pair of distribution. So our main observation is that if there's the algorithm that can exactly compute the indistinguishability spectrum, it's the best classifier that can classify the specific binary classification problem P. Of course, this P is built up out of the pair of distribution we are interested in. So our Eureka moment, that is to characterize such links. So I will not give a formal expression here, but the main idea is to find the equivalence that the algorithm that can exactly compute the indistinguishability spectrum, then this algorithm can be turned into the best classifier for solving the specific binary classification problem P. And then a P says the following. So it's uniformly at random pick one of this distribution and the sample point according to this distribution and ask the classifier to label it. And then about the classifier means that the classifier which has the lowest error that has the highest accuracy among all possible classifiers. Okay. So basically, this link implies that if we can approximate the best classifier, then we can turn into a estimator that approximately computes the indistinguishability spectrum. So we use this link to propose our estimator framework. So it says like any binary classifier can be turned into a Pricey estimator. So any good universal classifier can be turned into a good Pricey estimator. So here universal classifier means that the classifier can do well for a large class of classification problem. So of course, for such classifier, we can turn it into a good Pricey estimator that can estimate well for a large class of mechanisms. So we further show that the KN classifier can be turned into a KN-based estimator, which satisfies all the desired property we want. And then we do some evaluation, show that the empirical estimate is tightly matched the actual privacy spectrum. We not only show this hold on the Laplacian and Gaussian, we also show it on the more complex machine learning algorithms such as random projection, approximate least square. So these two, the random projection, there are some TCS paper before show that it enjoys some privacy for free, but now we recover the actual bound. It shows that it's quite good. And approximate least square is a well-known machine learning algorithm, and then we first time show that it enjoys strong privacy for free. So we also show that the DP estimator can be used to do the DP auditing task. Of course, the DP auditing just require a lower bound, so we can do better. So for the future work, one way is to do the black box estimation of variant privacy concept. Some of the black box estimator are easy to extend, but some of other enjoy some non-trivial challenges like the FDP. I'm quite interesting to see how they develop. So another line of work is the black box estimation with improved accuracy and efficiency. And that might be two ways. First is you restrict the class of randomized algorithm you are interested in. And then another is to design the memory computation efficient and binary classification algorithm. Like the KN actually, I didn't say people doing the very large training data set based the KN algorithm. So it's very interesting to say how to improve it. And some other like a better understanding of instant-based privacy concept, because we can say that due to the nature of the DP definition, it seems it is impossible to estimate the DP property. But of course, it's possible to estimate the instant-based privacy property. But there's a problem like how does the instant-based privacy concept fit to the real-world privacy need? So that'll be super interesting. So please let me know if you are interested in any of this topic. And that's all. And then we'll open up for questions. Thanks.
Sharing about my work on a relaxation of differential privacy known as metric differential privacy. This is a joint work done with Jacob and Kamalika while we were all at UCSD. Okay, so I believe by now you're all very familiar. Okay.
I think you're okay. I think they have to adjust.
Oh, I see. Okay. Okay. Wait for 2 minutes while this gets adjusted.
Just 1 second.
Yeah, sure. No problem. Okay. So I can start? Yes. Okay. So sorry for the interruption. I believe by now you're probably tired of seeing the same definition again and again, but oops, please bear with me as I show this definition one more time. So the standard differential privacy, it's bounds the ratio of the output distributions of two data sets that differ in a single row. Now let's pivot a bit and look into relaxation of this definition called metric DP. Here we have two differences from the previous slide. First, I'm working with single inputs. Oh, okay, my clicker is not working. Sorry. Something weird happened. My clicker is not working. Okay. I will use. No, but I think mine is not working. Okay, maybe I'll just use. Yes, okay. So let's look at our relaxation. I think I have to unmute myself. Sorry, there's so many technical issues here. Okay. So let's look at a relaxation of the definition called metric DP. Now here I have two differences from the previous slide. First, I'm working with single pairs of inputs, which means that I'm assuming that the data sets are singleton. Now, this is just for the ease of explanation. This simply corresponds to the local model of differential privacy. But the more interesting difference is the privacy parameter in the equation. Now we have a distance metric over the input space, and the privacy parameter scales linearly with the distance between the inputs. So what this means is that metric DP gives heterogeneous privacy guarantees for different input pairs. Intuitively, only inputs that are close or similar to each other are protected. So why should we care about this relaxation? First, it results in a more nuanced privacy guarantee. Metric DP tailors the privacy guarantee to the changes in the data, and this captures the natural privacy semantics of many real-world examples. For instance, let us consider the location of Tom Cruise. We all know he is an actor. His profession is public information. So revealing the exact city of his residence, which is LA, is not really a privacy violation because this is implicit from his profession. However, revealing the exact block of his residence, that would be a privacy violation. The other advantage of metric DP is that we get improvement in utility. Intuitively, this is because we require less noise because we don't need to protect against all pairs of inputs. Now, prior work in metric DP has focused in a setting which is known as the item level DP. This is the traditional DP setting where we assume that every user contributes only a single data. But as we saw earlier today, this is quite unrealistic in practice. There are a lot of scenarios when a user contributes multiple data points. For instance, for location, you would be collecting an entire trajectory of location, not just a single location. User-level DP seeks to provide protection at the entire collection of data of a user. To this end, this is the first work to look at metric DP at the user level for a general setting. So the first question is, what is a good metric to measure the similarity of an entire collection or set of data? The similarity of a collection or set of data has to be measured along two dimensions. First, we have to consider the difference in the distance of the different data items. In addition to that, we have to also account for the quantity by which these two data sets differ by. This necessitates a metric that can express both as a single measure. We tackle this by using the Earth mover's distance. The Earth mover's distance, which is also known as the van Wasserstein distance metric, measures the similarity between two distributions. Informally, it is the minimum cost of transporting one distribution to another, and the cost is a product of both the quantity of the data that is changed as well as the distance by which this change occurs. And this distance is measured by any underlying metric. Now, the picture shown on the right is an illustration of the Earth mover's distance. The blue dots and the orange dots represent two distributions, and they are paired together in a way to minimize the Euclidean distance between them. Now, let us see an illustration of the resulting privacy definition. We again consider a data set of locations. It's daily locations of users collected over an extended period of time. Now, under Earth mover's distance, we will be protecting against location pairs that are close to each other and collected over a smaller window of time. So let's understand, what does this mean? Locations collected over an extended period of time, say a month, would typically reveal routine patterns of an individual, while locations collected over a smaller window of time, say a day, reveals non-routine patterns. So why do we have a meaningful privacy guarantee here? Let's again go back to the example of our favorite movie star, Tom Cruise. If we look at Tom's location over an entire month, then it will most likely reveal that he makes routine visits to the Paramount studio. Now, this information is again implicit from the public fact that he stars in Mission Impossible movies. So this is again not a privacy violation. However, if we were to know of his non-routine visit to a rehab, now that would be sensitive information. So now we are ready to formally define our privacy guarantee. As I motivated here, the users contribute multiple data points, and the global data set is a collection of all the records of all the users. Our neighboring data set here, which is the two data sets that our privacy guarantee protects against, they can differ on the entire data of a single user. The Earth mover's distance metric dp then just states that the privacy guarantee scales linearly with the Earth mover's distance between these two data sets. Now, a couple of notes here. We assume that the distance is computed over the normalized data sets. Additionally, we also assume that the underlying metric is normalized, which means that the Earth mover's distance is always less than 1. Throughout the rest of the talk, I will assume that the total number of users, n, is fixed and publicly known. Now, we can have two different flavors of our privacy definition. If the size of the individual contributions of every user is fixed and publicly known, then we work in the bounded data setting. Alternatively, if an user can contribute an arbitrary amount of data and the size of the contribution is also private, then we refer to it as the unbounded data set. Given this privacy definition, we make the following contributions. We provide mechanism designs for two classes of queries. In the interest of time, I will be covering only one of them, item-wise queries. So here we are working in the bounded data setting, and our goal is to perform a private query A on each item of the data set. Now, this mechanism of private query A can be arbitrary. The only requirement is that it should satisfy the standard item level metric. The algorithm is very simple. We just apply A to every data point and release a shuffle. We shuffle the results and release them. We are able to show that the proposed algorithm satisfies Earth mover's distance metric dp with a privacy parameter that has a multiplicative factor of m, where m is the data set size. Now, the key idea here comes from the last step of shuffling the data. This allows us to leverage privacy amplification by shuffling result. So privacy amplification by shuffling is a beautiful result in standard DP. And Kunal also talked about it a little bit in his talk today. It says that after collecting the noisy responses from individual users, if we shuffle it, then we can do a tighter privacy analysis. Specifically, we can reduce the privacy parameter by a factor of 1 by square root n. For our analysis, we are actually able to provide a more generalized version of this privacy amplification by shuffling result. And we believe this can be of independent interest in the field of metric. Now, for the time being, I have just focused on the bounded data set. But recall, in the bounded data setting, it assumes that the size of the individual data sets is fixed and publicly known. Now, this can be quite restrictive in practice. We make a separation between these two settings because the privacy analysis is much simpler in the bounded data set. Nevertheless, we can get rid of this restriction and we provide a black box reduction for any bounded data mechanism to an unbounded one. In the interest of time, I will not be going into the details of it, but please see our paper if you're interested. Now, let us look at the utility of our proposed mechanisms. For this, we instantiate our general purpose mechanisms with specific concrete queries and compute the precise utility. Now, recall that the earth mover's distance is bounded by 1. So a direct implication of this is that we can set our privacy parameter to be large in practice. And this gives us utility improvement, specifically for the class of linear embedding queries, which means that the data is also associated with an embedding space. We can show that we can always achieve an improvement in utility as long as we can set our privacy parameter, the privacy parameter for earth mover's distance metric dp, to be greater than that of standard dp. We can do histogram estimation using the algorithm for item-wise queries, which I discussed. For this, we can get an improvement in utility if we set our privacy parameter to be larger than epsilon squared k, where k is the size of the data domain. Now, one thing I would like to mention is here, I just focus on the central model of DP, but we also have results in the local model of DP in the paper. So in conclusion, here we saw a relaxation of differential privacy called metric DP. Standard DP considers all pairs of inputs to be equally sensitive, whereas under metric DP, only similar inputs are considered to be more sensitive. And this results in a nuanced privacy definition. We also saw that for some practical settings, like the location data, DP's worst case assumption that the inputs are always completely different from each other is perhaps unnecessarily stringent in practice. And this is exactly where metric DP shines. It can provide advantages like simple mechanism design and improved utility while still providing meaningful privacy guarantees. And to the best of our knowledge, this is the first work to look at metric DP at the level of the entire collection of a user's data. Thank you very much for listening to me today, and I will be very happy to answer any questions.
I have one question. So I was wondering how specific are these mechanisms to the Earth movers, the distance metric, or why did you choose that distance metric other than the other?
Yes, so we chose the earth movers distance metric because recall that we want a metric over the entire collection, like a set of data.
Right.
And earth movers distance can capture two things. It can compare two distributions. It can not only capture like the raw difference in the distributions, but also the structure of the distributions. And this results in a flexibility of interpretation, and we can give like more rich privacy semantics. Thank you.
Am I good to go, Harish? Okay. All right. I'm Alex Beanstalk, and today I'll be talking about the distributed matrix mechanism for federated learning using PAC secret sharing. And this is joint work with Ujwal Kumar and Antigone Palakroniadou from JP Morgan as well. Okay, so what is the setup for federated learning? So you have a bunch of clients who have some data locally on their devices, and there is a server who wants to use this data to somehow train a machine learning model. And so what happens is every so often the server selects a subset of the clients, gives them the current model parameters, and then the clients locally train this model for some steps on their data, and then upload somehow their updated local model to the server, who then somehow aggregates them and sends the new updated model to the next set of clients. And we repeat this until we get some final model. And yeah, there's been lots of attention both in academia and industry for this recently. I was under the impression that Google did in fact have some applications of this in practice, but maybe I'm wrong. And also, I believe Apple does as well. And yeah, so there's so differential privacy, as we talked about in this session a few times now, is sort of the main privacy notion in this setting. And yeah, I'm not going to go through the formal definition again, since we all probably know it at this point. But yeah, there's kind of two kind of main notions for DP. The first one is central DP. And in this kind of setting, more or less, the users just send their model updates in the clear to the server. Maybe they use a secure aggregation protocol, but like even from the secure aggregation protocol, it's very easy for the server to go back to the original user data. But then what the user does at this point is on these aggregated updates, he applies some noise before releasing the model. And so yeah, in this model, you have DP with respect to the clients who get the updated model and the final model, but unfortunately not with respect to the server. But a good consequence of this sort of model is that you can actually get very high privacy utility trade-off. And one main approach for doing this is the so-called matrix mechanism. Yeah, and this matrix mechanism works even without using privacy amplification, which we've learned from some of the talks in this session can be kind of hard to implement in practice, actually. So yeah, what's the setup here? So you're given some data stream over T rounds and some linear workload represented by this matrix A. And this matrix can represent something simple like prefix sums, which can then actually be used for training as well with some post-processing, or something more advanced like a representation of stochastic gradient descent. And yeah, you want to compute, of course, like A times X, but also add DP to this. And so what they do in this technique is first they somehow factorize this matrix A into two matrices B and C. And what you end up releasing is this A times X hat. And here you first take the C matrix and multiply it by X, and then add some noise to this, and then multiply everything by B. Okay, and yeah, the main intuition here is that, sorry, and I should say you're releasing like one element of this AX hat at a time, like for each round. So you're doing this in like an online fashion. And yeah, so like the main benefit that you get here is from this multiplication of B times Z, you actually get that the noise is correlated across rounds, which kind of intuitively means that you can use less noise per round when you're sampling in an individual round. And yeah, kind of in terms of accuracy, what they want to do is, of course, minimize the loss of this factorization, which is kind of proportional to the size of B, like some sort of norm metric times the same thing for C. And yeah, that's intuitively, of course, because B is multiplying Z. And the reason why you care about C is that you're actually trying to get DP for this inner mechanism CX plus Z. And so the noise is tuned to the size of C, because this is kind of like, yeah, how much X gets amplified in some sense. And yeah, as I said before, this is this has been shown to provide very high privacy utility trade-off, sometimes even higher than using privacy amplification. Okay, then there's also this other world of local DP, which we've talked about before in this session. And yeah, for the FL setting in particular, I mean, there's been many works on this, but like one recent work that has sort of put together all of the pieces of this setting, it was called the distributed discrete Gaussian mechanism from a few years ago. And yeah, here, as you can see, the intuition is that the clients add some noise locally before their updates are aggregated on the server side. And so yeah, the pros are that we get local DP even with respect to the server. But here, the noise is not correlated across rounds, and so we get worse privacy utility trade-off, even if we do use privacy amplification. And so yeah, what we do in our work is sort of try to get the both of both worlds. So yeah, to enable this matrix mechanism where we have correlations across rounds, we essentially use secret sharing to share the gradients or the local updates and also the local noise from round to round. So in a bit more detail, let's say that we have some packed secret sharings of the aggregated gradients of the past rounds up to round j-1, and the same thing for the noise up to j-1. Of course, we know these are linear, and so we can literally just, locally compute shares of AX hat for j-1, well, for j, but taking into account the first j-1 rounds. And then we can input to the secure aggregation protocol sort of the reconstruction of these shares along with the relevant information from this round. So the gradients and the noise from this round. Yeah, and yeah, the good thing here is that we're basically implementing the matrix mechanism, but we're still able to get local DP because the server only sees the output of the secure aggregation, which is, noisy. And there's also some benefits of using secret sharing to sort of transfer these gradients and noise from round to round securely. Like we also looked at other sort of approaches using encryption, for example. And yeah, one main benefit is that if there's an active adversary, so maybe some of the clients or even the server is malicious and wants to break the privacy of the honest users, because we're using secret sharing, the most that the server can do is just additive attacks. So like the most that the server can do is add some like delta J in every round to the output. And this can really just be seen as post-processing on the DP mechanism, which means that, like the adversary can't do anything to affect the DP guarantees. And another thing is we can tolerate dropouts in every round. Because we're using like a threshold secret sharing scheme. So let me explain the packed resharing protocol a little bit. So in iteration R, we have a set of users with their noise and gradients. They'll use packed secret sharing to secret share a vector of these values to the parties in the next iteration. And then we'll ask the parties in iteration R+1 to somehow efficiently reshare these values to iteration R+2 so that iteration R+2 gets shares of the original values that the parties in iteration R shared. And of course, we want to do this with as little overhead as possible. And in fact, we're able to do this with constant overhead. And I'll try to explain this a little bit. It would help. I don't know if, Okay, yeah, you can see my mouse kind of. So yeah, so for each party L, he has these shares ZJL from each user J of iteration R plus one. And essentially what we're gonna do is we're gonna do a Lagrange interpolation to basically reconstruct in the secret sharing space. And what I mean by this is each ZJL is really just a sharing of these zeta shares that the parties in iteration R plus one have from the parties in iteration R. And so, yeah, if we take these linear combinations over the sharing space, then what we see that we're doing is we're just reconstructing in the secret sharing space, as I said before. And so in the end, what the parties get in the iteration R plus two is shares of the original values that those parties in iteration R shared. And yeah, we can just keep on doing this kind of strategy across time. Okay, and so yeah, we ran some experiments for this actually. So first of all, for the privacy utility trade-off, this black line is from like the distributed discrete Gaussian mechanism, which just applies local uncorrelated noise in every round. And these blue and green lines are from our distributed matrix mechanism. Yeah, you don't have to worry too much about the difference between them. One is sort of like a more, the blue one is a more efficient factorization, which basically allows us to only have to keep track of logarithmically many secret shared values at a time across the number of rounds. And yeah, you can see that because we use the matrix mechanism and correlate the noise across rounds, we're able to get much better accuracy. In terms of like computational experiments, we also ran them. So yeah, first of all, we're using a moderately sized model of about 1 million parameters. And yeah, so here, like, we used some data from this Lerna secure aggregation protocol. In these secure aggregation protocols, they use like every round has like many clients, it seems, but also like the model dimension that they use is smaller, I think. So yeah, we had to extrapolate based on their experiments. But yeah, for this 20,000 client setting, yeah, you see that the overhead from the resharing protocol is actually quite small compared to what you already have to pay for the secure aggregation protocol. But even for the setting where we have a smaller number of clients per round, yeah, you can see that things definitely blow up a little bit. But like, at least for this more efficient Honecker factorization, yeah, you can see that maybe like a couple of seconds and like 24 megabytes is reasonable overhead to have. And yeah, that's it. Thank you.
What is the model you're training there?
This was MNIST.
What model?
Oh, it's like a CNN, like a smallish CNN model. Yeah.
Send the picture again and put all the figures in one.